Okay, because besides phrase structure or constituency structure, there is one other very popular grammar formalism, and this is called dependency grammar. So, in phrase structure grammars, we have words combine into higher level constituents. And this then gives rise to internal constituents, which sometimes are also called non-terminal constituents, because they are not directly related to the words, but they abstract over different sequences of words. And in dependency grammar, in contrast, we're only dealing with the words and how they relate to other words. So the dependency relation is a binary relation which says whether or not two words are in relation with each other, and it's not a symmetric relationship, it's an asymmetric relationship where the role of the two words is different. So one word is the head and the other one is the dependent, and there are also other terms for those two words. For example, the head is sometimes called also the governor. The head of the whole sentence is usually considered to be, in linguistic theory, the finite verb, the finite main verb of the sentence. And every other word in the sentence depends on this finite verb, either directly if they are directly in the dependency relation, or otherwise indirectly through a path of dependencies. And as with the phrase structure parsing, there are multiple different linguistic theories which may yield slightly different parsing outcomes. So let us look at a concrete example which we have previously seen. I shot an elephant in my pajamas. So, as I've said, the main verb of the sentence, the inflected main verb, the finite or inflected main verb of the sentence is usually considered to be the head of the whole sentence. So we would say that okay, so here's a so we would indicate, so this is this verb here is the head of the whole sentence. Then this verb has its dependence, namely I. So this is the subject of the sentence. And we have further dependency relationships. For example, that elephant is governing the determiner. That shot is governing the elephant, because elephant is the object of the verb, so I shot the elephant. Then we have that pajama is governing the pronoun my. It's also governing the preposition in. And then we have two possible options. The first option is that the shooting is governing the pajamas as with the relation of a modifier. So the shooting happens in my pajamas. Or the other option is, and that was what the picture was related to, the elephant governs the pajamas. And now again we see that each word in this sentence is related to the main verb, which is shot, either directly, so we have three instances of words which are directly related, or indirectly. For example, the word in is governed by pajamas, which depends on shot. So this is an illustration of dependency parsing, and as you see here right away, we do not only have relationships between the words, but we also have typed relationships, so that for each relation we also have a label what this relationship means, such as subject, object, modifier, or other types of relationships. And note that there are, as I've already indicated, different formalisms. For example, the universal dependencies, whose goal is that the formalism should work across all languages, ideally, would have such a structure, but there may also dependency grammars that would, for example, say that the shooting is not governing here this noun, but it's governing actually the preposition, right? And maybe such formalisms are more language specific. Importantly, the dependency structure constitutes a graph. So you see, we have the sequence of words, and these can be considered as a graphs where each word here is a node. So we have nodes, and those stand in a asymmetric relationship with each other. And one could also say that this is a particular graph, namely it's a tree, and the property of a tree is that it's connected, so you do not find elements which do not connect to any other parts of the sentence. So for which there is no direct or indirect relationship, we do not find something like this. And also, it is acyclic. And acyclic just means if something is governing something else, the something else cannot also govern the original word, right? So if shooting, or if like shooting governs the preposition, then the preposition cannot govern the shooting. So that's what acyclic is meaning. And you can, of course, acyclic also means there is no such direct relationship, and there's also no indirect relationship where shooting governs in, and in governs pajamas, and then pajama governs shooting, for example. That also does not exist. So in the Stanford Universal Dependencies, the set of edge labels, so these types of relationships, are given as follows. So the subject and objects, that's what you know from school, like each sentence has a subject and object. In a Stanford dependency parser, that is written as n-sub, and the object is written as d-obj. However, there may be language, so those dependency relations are in Stanford dependency are language specific, so you have different ones for English than you have for Turkish or German. And when we go to universal dependencies, one tries to map those relationships to universal relationships that are valid across different languages. So maybe, and this results in different terminology also. For example, the n subject becomes SBG. So how do we parse in NLTK, how do we parse a sentence into its dependency relationships? So what we can do, similarly as with the context-free grammars, we can specify our grammar directly by giving the types of relationships that may exist between words. Maybe not the types, but giving which words may stand in a head dependent relationship. So we can specify this. We can say shot may govern I, shot may govern elephant, shot may govern in, and we feed this string into an object that is called the dependency grammar. And then if we have this grammar, we can feed our grammar into the NLTK object projective dependency parser, and we can apply then this object to parse any new sentence. For example, the sentence I shot an elephant in my pajamas, and it will give us the possible alternative interpretations of our input sentence given our grammar. And in this particular case of the shooting of the elephant, we would have that in the first interpretation, I shot the elephant, and the elephant was in my pajamas. And the second interpretation is I shot something, and what did I shoot? I shot an elephant, and how did I shoot it? I shot it in my pajamas. Okay? So now if you look at this grammar that we specified here, you might argue that it is compared to the context-free grammar or the constituency grammar that we've shown previously, it's somehow more unrealistic, because in this phrase structure grammar that we had previously, we could use those non-terminal symbols like as expands to noun phrase and verb phrase, and those may very generally hold, whereas those relationships are very specific, right? And they are kind of also unbounded. So you can, like if you have 10,000 words, or if you have 1,000 words, you can get 1 million relationships between all possible words. So this seems to be kind of arbitrary and unbounded. However, what we could do in reality is we could use an annotated corpus with dependency annotations to infer which words can actually stand in a relationship with each other. So these still will be quite a few words, but certainly not unlimited. And then we have a decent grammar. If, for example, we have a corpus of, let's say, 10,000 or 20,000 sentences, we would get a decent grammar with which we can parse, let's say, a good majority or a good subset of those sentences that we would encounter in reality. Good. Let's to conclude with dependency grammars, let's put dependency and phrase structure grammar in relationship. So in a phrase structure grammar, or like context-free grammar or constituency grammar, we have that we have the constituents of, let's say, a particular phrase, such as a preposition phrase. If we say that the immediate constituents are a preposition and a noun phrase, then we're also implicitly appealing to the head-dependent distinction. So in this case, we would say a prepositional phrase is a phrase whose head is a preposition, so that the preposition is actually the head, and its governor, and it's governing the noun phrase, so that the noun phrase is the dependent of the preposition. So the key point here is, although phrase structure grammars appear to be very different from dependency grammars, they also implicitly recognize those dependency relationships in a way. So we would have to, for each production rule, we would have to find out which element is the head in a production rule, and then we would say that this head is actually governing all of the other elements in the production rule. Okay, let's finish up with a brief outlook on grammar and historical grammar development. So one big problem in grammatical analysis and syntactic analysis is that if you have a high quality and high coverage grammar, that means it really covers many phenomena of your language, such as English, and in addition you have very long sentences, then you will have very, very many different possible path trees for each input sentence. In fact, the growth may even be exponential in the length of the input sentence. So this is because of ambiguity. For example, if we have a broad coverage grammar, then there will be a lot of lexical ambiguity. For example, A is not only a determiner, but it can also be a noun. Dog is not only a noun, but it can also be a verb. Runs is not only a verb, but also a noun. And this in English, especially in English, happens very often, that a verb can be a noun and vice versa. So if, of course, everything can have different part of speech, then everything can also be a noun phrase or a verb phrase, for example. So you will end up with very, very many different analyses of each input sentence. So how can we deal with this ambiguity? One solution that people have come up with in the end of the 1990s and the early 2000s is to use probabilistic parsing, which allows us to rank parses of an ambiguous sentence. Assume you have a sentence and 1,000 possible parses. You would like to attach a number to each sentence, like 0.2, which gives the likelihood that this parse is the correct one with respect to the evidence given in the training corpus. So in a probabilistic context-free grammar, we're actually doing this. To each production rule, we're associating a probability. So for example, that a verb becomes a transitive verb or a noun phrase, the probability is 0.4. That a verb expands to an intransitive verb, the probability is 0.3. And that a verb phrase expands to another subcategory of verb and a noun phrase, the probability is again 0.3. Note that these numbers here for each left-hand production rule add up to 1 because it's a probability. So something must happen. Some production rule must be applied. So then if you have the probabilities for each of those production rules, you can also calculate the probability for the whole parse tree by just multiplying each of those individual production probabilities. In NLTK, you can get a probabilistic parse by invoking NLTK Viterbi parser, feeding in your probabilistic context-free grammar as above, and then for an input sentence, it would not only give you an analysis but also the likelihood. So actually, the parser would be responsible for choosing the most likely syntactic analysis for you, so that you would not have to deal with, let's say, 10,000 different analyses. Another development in the grammar production is a tree bank. So, for example, the Penn tree bank corpus, which was developed in the early 2000s, that includes a lot of pre-parsed sentences, let's say in the context-free grammar formalism. And if you have such a corpus, then not only can you get the production rules but also their probabilities, and you can actually induce a grammar from your corpus and even a probabilistic grammar from your corpus. Good, here are a couple of links that I will not go much into. The Stanford parser is very popular and it's like a state-of-the-art parser. There's also the Stanford dependency for dependency relationships. There are some older parsers such as the MALT parser, the link grammar parser. Keep in mind that those parsers are not the current state of the art. The current state of the art is based on neural networks. So if you want to use the latest development, just look out for the latest papers from 2020 or 2019 on dependency parsing or on context-free grammar parsing or on constituency parsing. But if you're just fine with an application, let's say to a linguistic problem, you may also be fine with using one of those older parsers. And here are still some website links to parsing and dependency parsing that you may consult as additional references. The take-home messages from today are: we've seen syntactic parsing, we've seen lexical and syntactic ambiguity, we've seen context-free grammars, we've seen how to parse context-free grammars, or how to parse constituency, how to do constituency parsing using recursive descent parsing, which is a top-down approach, and shift-reduce parsing, which is a bottom-up approach, which is more efficient on the one hand, but the implementation that we've seen also suffers from lack of backtrack, so that it's possible that not each sentence will actually obtain a parse tree, a parse analysis. We have density dependency parsing, where we only have relationships between words rather than those non-terminal symbols and production rules. And finally, we have seen how to tame the flood of very many different analyses for each sentence by introduction of probabilistic parsers. Why is all of this useful? Well, first of all, I have to say that initially, the NLP community has thought that we live in this hierarchy where we first solve lower level tasks and then we go up and solve higher and higher level tasks until finally we arrive at a semantic interpretation of a sentence. Nowadays, with neural networks, it's actually less clear whether we should actually do this or whether we should not develop end-to-end systems which only take the input string as input, so that a sentence or a document is input, and then internally do whatever analysis they think is necessary to solve any given problem at hand. So while at the moment it's really a little bit debated whether we need those intermediate layers such as parsing, there may still be useful applications of parsing. For example, as a grammar checker, if your input sentence does not have a parse tree or a parse tree with very low probability, then maybe consider rewriting it, and maybe even it may even be grammatically wrong. It can also be used for information extraction. Recall the last lecture where we have done this chunko with bioformat. You can of course get similar information by doing a more deeper level and more informed syntactic analysis. It can also be useful for machine translation or question answering. For example, in machine translation, we might first analyze the syntactic structure, then modify it for the target language. For example, in English, in French, the adjective usually comes after the noun, whereas in English it's the opposite way, and in German it's also we first have adjective noun. So you could rewrite the dependency structure in the target language and then produce the actual target language output. And finally, if you want to prepare for the next week, what you can do is go again, look at this lecture and the basic concepts and definitions. Go to the tutorial and check what is being done there. Do the exercises, and finally in the next lecture we're gonna do semantics. So and we're gonna use like an older and more traditional framework which is called FrameNet to do semantic analysis. If you want to check this out, you can already prepare by looking at this website. However, besides this more traditional, more classic approach, we're also gonna see how semantics is being done with neural networks in a very few and high level slides.